that is known as an interrupt descriptor table, or IDT. And like our GDT, we have a nice page on the OSDev wiki that can help us understand the structure of the actual interrupts and the interrupt table that we're working with. Now, inside of this interrupt table, we're basically going to have a bunch of different entries, just like we had with our GDT. And we're going to create structs for those, we're going to build up those entries, and we're going to implement them into our operating system. Now, the question is, what is really the purpose of an interrupt? And there's really two main reasons why we're working with interrupts. And the two main reasons are going to be for interrupt requests and interrupt service routines. So interrupt requests are going to be something that will typically come in through hardware. It's basically a request for the processor to interrupt its current operation or execution. Interrupt requests can come from a variety of different places. Some examples may be your keyboard, some different serial ports on your computer, and various different hardware components of your computer. So in order to be able to service these different hardware components, their communications with the CPU, we need to have some interrupt requests available in our operating system. Now, in addition to this, we also need to have interrupt service routines. And basically, these are the routines that are run when an interrupt is received by your operating system. So the operating system gets an interrupt. It needs to be able to do something with that interrupt in order to handle it. And the main ones that we're going to see in this video are going to be associated with errors in the operating system. So, for example, if there was a divide by zero error in your operating system, right now, if that were to happen, the operating system would just crash. It wouldn't do anything. It would just go back to the grub screen like we saw with our GDT errors. Now, that's not really ideal. In most operating systems, it will crash and give us the error that occurred. We could see this in Windows with the blue screen of death, and we could see this in other operating systems with things like kernel panics. Generally, what we'd like to do is display an error to the user to say, this issue happened, and here's the information about like the stack and the registers, that sort of idea. For this video, we're really just going to demonstrate the message to say, hey, this exception has happened, and here's what we want to do about it. So with that being said, let's get into the actual implementation. Now, a few things have changed a little bit from this code. I just put everything inside of this source file, that's source code, just to help to organize it. And for this video, I'm going to put all my interrupts code inside of its own folder. This is going to help me organize things a little bit more. You don't need to do this. It's just for me to keep track of everything. But we're going to create 3 files associated with interrupts. There's the idt.c, h, and s. S is our assembly code, which we need. This is our C code, and this is our header. So we'll start inside of the header. And like I said, like the GDT, we're going to have a struct for each entry inside of the interrupt table. And these entries are going to have a very specific structure associated with them, which you can see here inside of the OSDev wiki. You'll see here that, like the GDTs, we have an offset, which is divided up into 2 pieces. This offset is the entry point of the interrupt service routine. So it is the function that we want to call when the interrupt occurs. So interrupt occurs, we go to that offset and start executing. We have this P, which is the present bit, like we had in our GDT. It's set to 1 to say that the descriptor is valid. We have a DPL, which was also present in our GDT. This is the 2-bit value that represents the CPU privilege level. We'll typically set this to 00 to have these at kernel level. We have this bit that's always going to be 0. We have a gate type, and a gate type is going to be something that describes the interrupt that we've added in. We're always going to see this as a 32-bit interrupt gate, so 0xe is the one that we're going to be using for these entries. We have a bunch of reserved space that we don't need to worry about, and then we have a segment selector. The segment selector allows us to specify a code segment in the GDT that we are going to use for this particular entry. So this is something that we're going to set towards a valid code segment in our GDT. So understanding that idea, we'll just put in our struct, and as with our GDT, we need to make sure that the ordering and the formatting is the exact same as the one that was specified in that wiki. That'll just make sure that we don't have any sorts of errors or problems with the formatting here. So I'm going to implement each of the different properties that I have. And this sort of thing is very similar to our GDT entries, so it's not really anything too exciting. It's pretty standard and straightforward. And we're going to, like before, set the attribute as packed for these. Okay? So that's the setup of the entries. Now, like our GDT, we are also going to have this pointer struct, which is going to, of course, point to our IDT entries. So this is the same sort of idea as what we had with the GDT. So we have a limit and we have a base. And this is, of course, going to have an attribute as packed.
AI is changing the game for app development. Firebase is here to help. Easily build AI-powered experiences into your web and mobile apps with speed and safety. Then launch, monitor, and iterate with AI-assistive tools that help you optimize your app's quality and experience. Firebase helps you run your app with confidence, deliver the best experience for your users, and get to market quickly and securely, doing what you love. Make your app the best it can be with Firebase.
Are you sick of sifting through job scams on job sites? At flexjobs.com, every job in our database is hand-screened by our researchers. And yeah, there's a membership fee, but that's so we can pay those researchers to keep you safe in your job search.
Now for now, there are two functions that we're going to work with, one to initialize the IDT and one to set each of the IDT gates. This one is going to have a very similar structure to the GDT. It's going to have the index in the array where we're placing the actual gate. It's going to have the base value. It's going to have the selector values, the select values, and we're going to have the flags as well. So those are the three things we need to provide to it. And what we're going to do is we're going to do some bitwise operations to parse things out and get it into this format here, which we'll see as we're going through. So I'm going to go ahead and copy these over to idt.c, just that way I have both of these function descriptions in and available. And then we'll get to work with our implementation. Okay, great. So in order to set this up, we're going to need a few different things included. We're going to include our standard int. That way we get over like uint formats, these types of things. We're going to include the util.h. So we need some utility functions as we're working through this. We're going to need some VGA functions, so we'll include our VGA header. And of course, we'll include our IDT. There's two structs that I'm going to initialize here. We have the IDT entry struct, which I'm going to call IDT entries. It will have 256 in size as the array. So there's going to be 256 entries in the IDT. Not every single one of them is going to have a value, but some of them will. So we'll see how that is structured out. And I'm going to define the struct for my pointer, which is just going to be called IDT pointer. Okay. And then I'm going to create an external reference to a function called IDT flush. This is similar to the GDT flush. It's going to be some assembly code that's going to essentially set up all of these different records that we're creating inside of the IDT table. Now, there's a few interesting things that happen with our IDT. The very first thing that we're going to do is set up the limit of the pointer and the base of the pointer. This piece is quite similar to our GDT table. So we're just going to get the size of each of the structs and multiply it by the size of the array. So these two numbers here are going to match with each other. And then we subtract 1, just like with the GDT. Similarly, when we set up the base, we're just taking the address of IDT entries. So the address of this array right here. And then what we're going to do is we're going to initialize everything to 0 using memset. And that's because we're not going to set a value for every single entry here, but we do need the total number of entries initialized. So we're just going to initialize everything to 0 and then set the ones that we actually need. So this is going to be the size of the IDT entry struct times 256, just like that. Okay. So all of this is very standard, straightforward so far. This is where we get into the interesting part, and it's the fact that we need to actually do some programming for what we call Programmable Interrupt Computer, or PIC. So in your computer, there are two PIC chips, and generally they'll have different namings for them. I think like the standard naming is that one of them is called the master chip, one of them is called the slave chip. You can also refer to them as the main chip and the secondary chip, whatever you want to refer to it as, but you'll see those terminologies generally used for these chips. Generally, one of the chips is going to sit at memory addresses 0x20 for commands and 0x21 for data. The second chip is going to set at 0xa0 for commands, and it's going to sit at 0xa1 for data. Now, these will need to be initialized in order for us to be able to use our interrupts. So we need to actually send some data to these chips. Now, how do we send that data? Well, we have to use a special command, which I'm going to set up in this util.c. That special command is going to be called outport b, that's what I'll call it. It's going to take in a value for a port, and it's going to take in a value. And what it's going to do is it's going to run the following assembly code. It's going to run the command outb, %1, %0. And then for the syntax, we put this. And then we put the formatting of our value for the port and our formatting for the value. So you may not have ever seen this operation before. I never really talked about it in the x86 video so far. What it does is it outputs a byte of data to a specified I/O port. So what happens is all of these different ports on your CPU could be hooked up to different chips. So one of them is hooked up to those PICs. And what we're going to do is we're going to write data to the port that's hooked up to those PICs so we could send data directly to those chips. That's the idea of what we're doing with this port value setup. So we're writing to the port associated with those chips a specific value. And that value is going to be for the initialization of those chips so we could set them up for our actual interrupt creation. Okay? So that's what we're looking to do here. So that's what this function's purpose is generally going to be right now. The reason why I put it in util is because we will use it in a variety of different places, not just in the IDT. So we are going to set it up here and then just import it wherever we need it. So as I mentioned, these different ports are going to be associated with each of the different areas on the chip. So to get this to work, what we're going to do is we're going to run outport B. And the very first thing that we do is we send 11 to the command ports of each of our chips, the primary and secondary ones. So we send 11 to each of those chips. This is going to start those chips up into their initialization mode. So now they're waiting for, I believe, 3 more commands they'll accept. And each of those commands represents something specific. It's going to give it an offset, and then it's going to give it the location of each of the different chips and initialize those. And that is going to get us all set and ready to go. So that's the first set of commands that we need to do. Second set of commands that we're going to do is the following. We're going to send to the data section of the first chip the value 20. And then we're going to send to the data section of the second chip the value 28. So these are what are referred to as the, I believe, vector offsets. So it's setting up those offsets for our chip. And then we're going to send a few more requests out to these data sections. Okay. So again, we send off to each of the data sections. In this case, the values 4 and 2. And then we're going to do a few more data section sends. So we have another set of those here. So we send to 21 0x01, and then we do the same with 0xa1. We send it 0x01. And then finally, as the last sort of thing, we just send zeros to each of these different chips. Okay.